All right, let's take some questions here on any of those that you tried, any of these use substitution ones. Maybe we can work through some of those. The gateway test is going to be on Tuesday. Okay, that seemed to be the consensus.
I thought we said Wednesday.
So yeah, you're right. Yes. Which one?
No, I did it, but I got a different answer. 31. Yeah, I got it. I got 31. I got it.
All right. What's wrong with Tuesday? Just because it's earlier than Wednesday? You have another test on Tuesday?
It's true. I have a bone.
Yeah, we haven't
named all the
bones.
bones.
Yeah, like all the bones.
Ryan, have mercy.
Maybe Mondays.
Whoa, whoa. Well, we are going to have a lot of review tomorrow and a lot of review on Monday in class. I mean, so in other words, I'm going to put up some problems and just, do them, and then let's check them, do some more, check them, do some more, kind of like practice gateway testing. We'll do that a little bit tomorrow. We'll do that a lot on Monday, so that will help, hopefully. So yeah, probably still going to be Tuesday. We'll see. Yes.
Is this going to be like the other gateway test where if we don't simplify it enough, it's going to get...
No, that's the thing about antiderivatives is there really isn't anything to simplify. You know what I mean? Because you're right, on the derivative test it was follow the rule, and then you get this long big thing, and then you would kind of have to put some things together and simplify some things. On this one, it's really more, it's the reverse, isn't it? Remember we talked about how they're messy, kind of messier, at the beginning, and then like when you do your use substitution, then you get your new integral that you substitute is actually simpler, and then you just do it, and then you sub back in, and then you're pretty much done. So really, there isn't much of that. There isn't much of that simplifying thing at all. As a matter of fact, some of the hardest ones to do are the ones that aren't messy at the beginning. Like, Jamie asked about this one, 51. I don't know how many of you tried this one, but it's this right here, right? And so what's confusing about that one is there's nothing really to substitute. I mean, it's too simple at the start. It's almost easier when there's more stuff because you can pick what to let u equal. So what do we do on one like this? Well, if we look at page 333, okay, those are derivative rules, but if you look at the derivative rules and look at the right-hand side, there isn't anywhere where tangent is over here, right? I mean, we're supposed to know these rules. So the antiderivatives I told you should know, are all these here. Well, tangent's not. That's not good. It did. Well, that's never happened before. That's weird. Huh. Okay, well, let's go back to this. All right. So anyway, it's not on there, right? The antiderivative tangent's not on there. So when, like some of you I noticed you started with number 23 and you just went 10 right down the line. Now that's okay, but you notice they're kind of grouped. Like there's a bunch of algebra type ones in the beginning, like with a bunch of X's. You go over to the other column over there, and then you get a stretch where there's a lot of some trig ones, or you get some E to the X ones, whatever. So it's good to get a mixture of those different types, right, to work on, because there will be a mixture. So 51 is tangent. Well, what you can do with the trig ones sometimes, if there's nothing real obvious, is do some sort of trig identity, and basic trig identities, like the secant is 1 over cosine, or tangent is what? What's another name for tangent? Sine over cosine. So the way to do this one is to actually change this into sine over cosine. Okay? Now, what what could you let the u equal? Cosine of x? Well, no, let's think about it. Could you let u be cosine, the bottom? Now, we've talked about letting u be the inside. Haven't we let u be the bottom sometimes too? What do you get if you let u equal cosine? Remember your next thought? What's the du? The derivative. What's the derivative of cosine? Negative sine. Now, the negative we can deal with, so we don't care about that. But you'd have negative sine x dx. Is there a sine x dx setting there? There is. Now, some people might say let u equal sine. Would that be okay? If you let u equal sine, what's the du? Cosine x dx. Is there a cosine x dx setting there? No, there's not a cosine x dx. There's a 1 over cosine x dx setting there. But that's not what we want. We want a cosine. So letting u be the bottom is actually what you want. So you're going to let u equal cosine x here on this one. And then du is going to be negative sine x dx. So you do have to be a little creative. Remember we said antiderivatives is more art than science, right? Sometimes you got to be a little creative in what you do. Now, that's why practice is so important. The more you practice, the more of these little tricks and little things that you'll see, that you'll run into. Okay, they're just, I can't give you every single possible situation that may arise, but we can certainly try to attack as many as possible, right? And the more of this page you do, that's why I said a minimum of 10. So if you did like 4 of them, well, okay, you got good practice on 4 of them, but the chances of hitting all those different scenarios that might come up is not very good, okay? And then you're going to be relying on other people to ask questions on some, that they may have that might help you. All right, so let's move the negative over there. But I know the other class told me it sounded like there was big intramural games or something last night, so that may cut into some of your time. I know that. You know, they were complaining about the homework you did for last night because big intramural games last night. But anyway, so we got the negative over here, and then that's kind of why I asked what was bad about the gateway test next Tuesday. I thought maybe it was because of intramurals or something. But the championships aren't those coming?
I think the semis are
Semis are like
on
Monday.
Monday.
See, I know. So that is an issue. I know. All right. So anyway, so when we sub, what will we have? On the bottom we'll have u, right? On the bottom we'll have u, which is that. And then this sine x dx is negative and du, so there'll be a 1 there, right? And so what's the antiderivative of that? Natural log of u plus c, and then put your cosine back in. Now, some book, I remember when, barely when I was in college, barely remember. But we could have made a longer list. Like, page 333 could have been longer. We could have memorized this, right? We could add this to our list of ones to memorize. We got antiderivative sine, we got antiderivative cosine. We could just memorize antiderivative of tangent. Is negative ln cosine x plus c, right? I mean, you could add that to a list if you're good at memorizing and want to do that. I mean, it makes sense. We got sine and cosine. We know they're antiderivatives. Why not do tangent? But it can be done by just making tangent be sine over cosine and pick a convenient u at the bottom and just do it, right? So you do that. Now, was it 50 or 52? 52, the very next one. While we're talking about this, let's look at that. Okay? So 52 is the antiderivative of secant x tangent x. Anybody know right away what the answer to that is? No? It's the antiderivative of secant x tangent x. Is there some function that when you do the derivative, it equals secant times tangent? Secant. So this is just secant x. If you know your derivative rules, which we're really supposed to, and this is still frozen. Now, I'm not sure on Windows how to... Well, I'm trying. Like up here. Oh, whoops. What was that? Okay. right, so that was the derivative rules. Okay, there we go. And then I'm not sure, where do I have my derivative rules? Probably in chapter 3. There we go. So if you remember your derivative rules, then right here is the antiderivative of secant tangent. The antiderivative of secant tangent is secant, right? And that was one of the rules that we were hopefully gonna have memorized. We didn't run into it very often. That is true. So it's not a bad idea to look at some of those. Now I've told you the emphasis will be on arc sine and arc tangent, whatever. But if you didn't memorize it, then you would do a U substitution. The answer is secant, right? But we could change this into sines and cosine. So this would be 1 over cosine times sine over cosine, right? So this would be the same as sine x over cosine squared x dx. So now maybe I would just give you this, to be honest. So let's do this one. So I might, on the gateway test, just give you that bottom version. Instead of giving it to you as secant tangent, I might just give it to you as sine over cosine. Sine over cosine squared, like this. I might just give you this problem. Okay? Well, what would you let u equal here?
Cosine.
Isn't that on the inside? Because remember, cosine squared is actually cosine of x all squared, right? So cosine of x is actually, cosine of x is actually our inside. And not only that, but what's the du, the derivative? Setting right there. Negative sine x dx. Let's move the negative over there. Divide by that negative 1 and be negative 1 over there. I get sine x dx. And so look at my substitution. It's going to work right nicely. The top, sine x dx, is just going to be a negative and a du. And then what's the bottom going to be? U squared. 1 over u squared. Now is that an ln? No, that's not an ln. That's u to the negative 2. So how do we do that? Raise it up 1 to negative 1 and divide by negative 1. Well, that negative 1 we divide by will cancel out that negative. So it's just going to be u to the negative 1 plus c, which is 1 over u plus c, which is 1 over cosine plus c, what's 1 over cosine? Secant plus c, which is what we just got to say a minute ago the answer was going to be, was secant. So if you didn't memorize that secant tangent, the antiderivative of that is just secant. We just got it by doing u substitution. Now, I'm okay if you left it 1 over cosine. That's fine. If you just leave it 1 over cosine. Okay? So we can be done with the u substitution. All right, what else? What else did you run into that you had some issues with? 41? Okay, what's that problem? Integral?
Yeah, x plus 4 over x squared plus 1.
Ah, good one. X squared plus 1. Now, when I see x squared plus 1, I right away think of 1 plus x squared, actually. What does 1 plus x squared on the bottom make you think of? Arc tangent. It better, right? It better make you think of arc tangent. Here's page 333, right here. You have a 1 plus x squared or 1 plus something squared on the bottom. It could be a u squared. We do a u substitution. 1 plus something squared on the bottom should make you think arctangent. It's not always going to be arctangent. We're going to see that actually in this problem. It's not always going to be arctangent, but it should make you at least be thinking, hey, this could be an arctangent. Same thing with a square root of 1 minus something squared on the bottom. Should make you think of an arcsine. Okay? All right. Now, problem is, well, what's the problem with this being an arctangent? There's not a 1 on the top. Now, it's okay if there's not a 1 on the top. I mean, if I have 3 over 1 plus x squared, is this going to be an arctangent? What can I, yeah, it is. What am I going to do with this 3? I can just pull it out in front and then make that a 1, right? Because that's just 3 over 1. All that is 3 times 1 over 1 plus x squared, right? So if I have a 3 on top and then a 1 plus x squared on the bottom, that's an arctangent. Just pull the 3 out, okay? So you can do that anytime you have that number. So we talked about pulling out a 1/2, or if you have a constant in there, you can do that. So having a 3 in there, we can do that. But now, if you have an x up here, that's different, right? You can't pull out the x. Well, what if you had this right here? Now forget the +4. That's what makes this, the +4 is what makes this one tough. Was there one that looked like this? Was there one that didn't have the +4, that just had an x and had like a 1 + x squared on the bottom?
There's an x cubed.
There's an x cubed on the top, but that's kind of similar, right? But so those are not arctangent ones, right? So like on this one, what would you let u equal? Why? Because the du is going to be what? 2x dx, and there's an x dx setting right there. So see the thought process? So you're thinking to yourself, okay, if I let u, that looks like it could be an arctangent, but it's got an x up there. Oh no, if I let u equal 1 + x squared, the du will be 2x dx, and there's an x dx setting up there. That's what I want. That's what I want. So I do u substitution on that. Okay, so back to this one. So if there was just a 4 here, this would be an arctangent, right? If there was just an x up here, it would be a u substitution one. Well, what do we do if it's both things? Separate. Remember we talked about this? If you have a single denominator, now you can always have a single denominator. Let the 1 + x squared be the denominator. That's your one thing. If you have a single denominator and you have pluses on top, you can split it apart. So let's split this into the integral of x over 1 + x squared plus the integral of 4 over 1 + x squared dx. Because remember, when you split a fraction, as long as you keep the denominator the same, you can always add it back together because you add up common denominators. So x over 1 + x squared plus 4 over 1 + x squared is the same as x plus 4 over 1 + x squared. See, the reason that you had to do that, think about it. If you'd have let u equal 1 + x squared in the beginning, then your du would have been 2x dx. Now you could have divided the 2 over here, but now you end up with just an x dx. The 4 is in the way. You can't pull that 4 out because it's addition, right? If there was a 4x up there, then yeah, if that was 4x up top, we just pull the 4 out. We'd be fine. But plus and minus always throw a wrench into those things, okay? And so this would tell me, oh, I can't do this. This +4 is in the way. Well, this is what you do if you get plus on top, or it's one thing you can do. So again, it's another one of these little tricks that you're only going to know by practicing a lot of problems, right? And you're going to see, oh yeah, okay. And so next time you see something like this, you'll be like, oh, okay, I remember this. I did one like this, so this is what I want to do. So on this one, we're going to do a u substitution. So we're going to let u equal 1 + x squared. The du is 2x dx. We're going to divide the 2 over, and we got that. So now my new integral, the 1 + x squared is just going to be u. The x dx is going to be 1/2 du, and we'll have a 1 on top. So there's an ln. So we're going to have a 1/2 ln of u. Somebody asked me if they had to always do the ln u, or put the u in, then sub in. No, you can do this all in one step right now. I know this is going to be ln u, and u is that. So bars 1 + x squared. Oh, this is one of those, do the bars really need to be there? 1 + x squared will always be positive, won't it? So the bars don't really need to be there, but you can have them, that's fine. Okay, now let's do this one. This one we said we're just going to pull the 4 out. Make that a 1 there, pull the 4 out, and that's just arctangent. So that I don't have to do any u substitutes. That's just going to be 4 arctangent x plus c. It's always arctangent of whatever is squared down there. But since it's just x, right? Sometimes we turn that into a u. We have 1 + u squared, so we can get an arctangent. Okay? Well, you've never seen that before, where we split one that looks like that. But that's what you're going to do when you have polynomials like that up there. Okay? But it's a really good one to look at these two different integrals. They look very similar, but the difference is having an x here makes all the difference because your du is there, so it subs out nicely. Not having an x up there makes it something totally different. It makes it an arctangent. Okay, so problems can look very, very similar and you handle them differently. So you've got to see those differences. Okay, what else? What else? What else?
How about 62?
62. What was 62?
X to the 4th.
X to the fourth times
Yeah.
the cube root, so that'd be the 1/3 power. So x to the fourth, and then what's in there?
X to the 5th plus 6.
Plus 6.
Yeah.
And that's to the 1/3 power. Like that. Okay? So what is our possible u? X to the 5th plus 6, the inside. And again, that's nice, it's good, because the du is going to be 5x to the 4th, and we've got an x to the 4th setting there. That's what we're looking for, right? We're looking for a u that we pick to have the du, the derivative, setting there. That's what's going to make it nice. So now we get into it, so we get 5x to the 4th. The 6 goes away, which is good. The 5 is in the way, so let's divide it over. And we got, oh, don't forget the dx. Whoops, so we got x to the 4th dx. So, substitution, the x to the 4th and the dx. Sebastian, we were talking about this. So on our substitution, so x to the 4th dx, which are those two, what are they going to get replaced with? Those two things right there. So our new integral, we're going to take those out, and we're going to put those in. So there's going to be a 1/5, and there's going to be a du, right? And then what's this thing, Sebastian? This thing right here. That's u, so that'll be to the 1/3. So in here we'll have u to the 1/3. So see, so back to Rachel's question about the simplifying. See, it's not. I mean, it's messy in the beginning, but when things are set up, which these are, I mean, these are determined here to be nice for u substitution, right? I mean, they're kind of set up for it to work nicely, and that's what many of the gateway ones. Now we got another technique to talk about today, but the ones that need u substitution, you know, they're going to be set up fairly nicely. Now the harder ones are the ones that don't look to be set up as nicely, like one like 41. Could that be under? Sure. Or one like this. It doesn't look, there's no obvious thing for u substitution. So if it's a trig one, you might want to change it into sines and cosines. Might be a strategy to use. Okay, but this one's pretty straightforward. Okay, we subbed everything out. So now we just raise that up one, which is what? 4/3, and divide by 4/3, which would be 3/4 u to the 4/3. Now my fear is that you'll get a lot of the calculus stuff right, you'll do a lot of the antiderivatives, and then you'll miss 3 of them that have fractions in them because you don't know how to multiply fractions, right? I mean, that's going to be on there, okay? I mean, I promise you, I mean, I've seen, you know, talking to college kids, a lot of college professors don't like using calculators, and they want students to be able to do a bunch of stuff without a calculator, like this gateway test is, and they throw a lot of this at you. They want you to be able to do these things. So we got to do a little bit of it. 3/20, you just multiply straight across on fractions. Just multiply straight across. Okay, 3/20, u to the 4/3, and u was that. X to the 5th plus 6 to the 4/3 plus c. So there's really very little simplifying, obviously, other than being able to multiply two fractions together. But once you get it, it's pretty much done. Okay, so that is one of the good things about the gateway test is you don't have as much reliance on those kind of things. Okay, and remember, when you raise this up 1, you're adding 1, so it's just 1/3 plus 3/3, right? I mean, or plus 4/4 or 5/5 or whatever that fraction happens to be. So when you add 1, you write that down. If it's negative, if this had been negative 1/3, then it'd been negative 1/3 plus 3/3. That's why it's 2/3, right? So, all right. Anyway, another one. 37. What was it?
X squared over 1 plus x to the 6th.
Okay, good one. So, because I was thinking this when we were doing that arctangent one earlier. So anytime you see a 1 plus some power, arctangent should be the first thing to come to mind. Okay, anytime you see square root of 1 on the bottom, square root of 1 minus something to a power, arc sign ought to come to mind, right? Now, let's see if you can tell the difference. What would you have wanted on the top in this problem? If the bottom was what it was, what would you have liked to have seen on the top for a really nice U substitution? X to the 5th, right? You'd have really liked to have seen an X to the 5th up there. If you this is that recognition part I'm talking about. If you see a problem like this, you see 1 plus X to the 6th on the bottom. If you got an X to the 5th on the top, man, it's just a simple U substitution, right? Because you're going to let U be the 1 plus X to the 6th. The du, the 1 will go away. You'll get 6x to the 5th dx, which will be sitting there, and voila. So since it's not there, since it's not x to the 5th, you say, oh, there must be something else going on, because that would not be good if I got x to the 5th and it's not sitting there. So then you would think of arctangent, right? And so what is x to the 6th? X cubed squared. Power on a power, you multiply. So what do you suppose our u is going to be? X cubed. Which, of course, the du is going to be x squared dx, which is what's sitting right up there. And so that's why it's going to be x. So the du is 3x squared dx. You divide the 3 over. And now your x squared dx is going to be 1/3 du. And this is going to be 1 on the bottom, 1 plus u squared, right? It's x cubed squared, and your u is x cubed. So that is an arctangent. And so it's 1/3 arctan of u, which, of course, u was x cubed plus c. Right? Again, easy one to check. The derivative of arctan is, so the 1/3 would hang out. The derivative of arctan is 1 over 1 plus this squared, which would be x to the 6th, times the derivative of the inside, which is 3x squared. The 3's would cancel, and sure enough, you would have x squared over 1 plus x to the 6th, which is what we started with. So it does work out. Okay? So we can check it right nicely. All right? Good question. Good question. All right, so any of those where you see those other powers, like if you have a 1 plus x to the 4th, what should be coming to mind is if that's x squared squared. So that's a u squared situation. Or x to the 8th, that's x to the 4th squared. Right? And so you're going to be running into those. All right. I can't think of two, I'm sure there's some other situations. This is always a big one that, this splitting it apart things, we'll be able to handle that. The trig things, okay, and so forth. So I want to give you some more time. I want to talk about this new thing, so let's do that right now. So get your notes out. This is basically the other technique we're going to talk about. Now, there are a lot of different techniques. There are a lot of different techniques for integration, but the rest of these go into Calc 2. Now, we're kind of we'll be getting into some Calc 2 kind of things, some college Calc 2, because Calc 2 usually goes up into basic antiderivatives, or Calc 1 goes into basic antiderivatives, integrals, right? And then that's kind of where it ends, and then Calc 2 picks up from there, right? So this particular section is actually in Chapter 8. So all we're doing right now is in Chapter 5. I've actually picked out this topic from Chapter 8 to do, because some books have it, some books do it earlier, some college Calc classes do it in Calc 1, some wait and do it in Calc 2, whatever. Okay, so we're going to go ahead and do it. Now, it's called integration by parts. But what it is the reverse of the product rule. So U substitution is really the chain rule in reverse when you have something on the inside. This is kind of comes from the product rule. Okay? Now, that doesn't mean that you're going to, every time you have a product, that's what you use, right? It's different. Remember, we don't really have rules for antiderivative. They're just the derivative ones in reverse, right? And so like U substitution is not really a rule, it's a technique. This is what you do if it looks a certain way. Same thing with integration by parts. If it looks a certain way, this is a technique you can do to figure out the antiderivative. It's still got a substitution component to it, okay? But what we do is we split it up into parts, and that's why it's called integration by parts. Then there's something called trig substitution. There's something called the method of partial fractions. There's a number of different techniques that we won't be getting into, okay? All right. This particular technique will not be on the AP test, the Calc 1 AP test that we take, that people take, or won't be on our final, okay? But it will be on the Gateway. Now, there won't be a lot of them. Most of the Gateway will be just straightforward antiderivative type ones, like we did one yesterday. You had to kick out a 1/3 or something like that. A lot of U substitution, probably half of it will be U substitution kinds of things. That'll be the emphasis, okay? And then probably a couple of these, probably no more than 2, right? If you're trying to use, and I'll say this many times between now and Tuesday, if you're trying to use integration by parts more than 2 times, you're using it too much, okay? Because I've seen people do that where they just start using this all the time, right? 2 at the most, probably on there. Okay? All right, so anyway, here's the product right here. So, right, derivative of u times v, u and v are both functions of x, just like what we're doing with u substitution. When we let u equal x squared, we're saying u is a function of x, right? So u and v are both, so if you have 2 functions of x multiplied together, this is how you do product, right? Now, we're going to undo this, right? We want to do this in reverse. So what I'm going to do is I'm going to do the antiderivative of both sides. So if I do the antiderivative of the left side, well, the left side is the antiderivative of the derivative. They should cancel each other out, right? We just get uv, right? This side, if I do the antiderivative of this side, it would be just like doing this, doing the integral with respect to x, right? All right, so I'm doing the antiderivative of both sides. So that gives me this. Now, this is weird. This kind of looks strange with those prime notations. We haven't been using prime notation, have we, when we've been doing this? Instead of writing u prime when we do u substitution, what do we write? Du over dx, right? So I want to change that so it looks like that. So I'm going to change my u prime into du over dx, and I'm going to change my v prime into dv over dx. So that's all I did on that step. Okay, just change my u prime to du over dx and my v prime to dv over dx. Okay? So started with the product rule, which is a derivative. Did the antiderivative both sides. That's what we're trying to do, is undo this. Okay? So the left side just became uv, and the right side looks like this. Now, it's a plus, so I can split this into 2 integrals, right? So I can split that into 2 integrals. So I'm going to do that next. Okay? So I split that into 2 integrals. Both of them would have dx at the end, right? Because I did the antiderivative with respect to x, right? Remember, u and v are both with respect to x. And what happens there in that first integral? What feels like should happen in that first integral? With the dx's. Doesn't it feel like they cancel, right? And they do. I mean, and over here also, in this integral, right? And that's right. And so, look what we got. Now, in this integral, I got du and v. We always like the du to be at the end, so I'm going to flip that. So I got integral of v du plus the integral of u dv. Right? That's what I'm left with. So all I did was just do some rearranging of the notation on that right side. So I started with the product rule, did the antiderivative of both sides, and then on that right side, I've just been messing with the notation is all I've been doing. And I end up with this. Okay, now, I'm going to subtract this one. I'm going to subtract this one over to the other side. So I get uv minus the integral of v du equals the integral of u dv. Okay? And now, finally, I'm just going to flip those 2 sides around. I want the integral of u dv to be on the left. I should have started it that way. So I'm going to take the integral of u dv and put it on the left. I'm going to take that other and flip it over to the right. And that gives me the formula for integration by parts. So you just have to memorize this. So what this says is if you have an integral and its parts, its two parts are u and dv. And you'll see what we're going to do with that in a minute. But if you've got an integral and its two parts are u and dv, the answer to that, or the equivalent to that, is u times v minus the integral of v du. Okay, what does that look like? See, that sounds weird. Well, here's what it sounds like. We need, so if we're given an integral where integration by parts is going to work, and that'll be part of what we're going to learn today, is how do we identify that integration by parts is going to work? Well, for us, it's going to be easy, because we only know two. U substitution, and now this one. So if U substitution won't work, it's got to be this, right? I mean, so that's the easiest way to identify that it's going to be integration by parts. If U substitution won't work, then it's got to be this, okay? So the key is, what we have to do is we have to pick which part is which. We have to pick one part to be U, and then whatever's left over is going to be the dv. Okay? So we're going to look at our integral, and we're going to pick one part of it to be U, and whatever's left over is going to be the dv. Now, if we pick something to be U, can we find the du? How do we find the du? Do the derivative, right? Because in our formula, we need the du, right? We need the u, whatever we pick for u is going to go there, and then we need the du to put there, and that'll be the derivative of it. And then whatever's left over is going to be our dv. But over here, I don't see dv anywhere, just v. Well, if I have something that I'm calling dv, well, how will I get v? Do the antiderivative, right? Now, hopefully, it'll be something I can easily do the antiderivative of, or else this isn't going to work, right? So I want the dv to be something I can easily do the antiderivative of so I can find v. And whatever v is, I'll put there and I'll put there. Now, you might be noticing, well, you mean we're going to have this integral we're trying to figure out, and it's just going to give us a new integral. Well, isn't that what u substitution did? U substitution turned our original integral into a new integral. What was nice about that new integral? It was easier. It was easier to do. Well, that's what should happen here. We're going to trade this integral. We don't know how to get the antiderivative of it. We're going to trade it for a new integral that hopefully we can do the antiderivative of. Okay? So that's how we're going to use this formula. So you just got to memorize your integral. We're going to pick part of it to be u. The rest of it will be dv. Then we find our du and our v, and then we just stick them into that formula. uv minus the integral v du. You just got to say it over and over and memorize it. uv minus the integral v du. uv minus the integral v du. Okay? All right. So, how do I know what to pick for u? How do I know what to pick for dv? Well, the dv is easy. That's just going to be the leftover. Right? The dv is just going to be whatever's left over. How do I know what to pick for u? Well, we got a little saying that is going to help us. Liate. Kind of. Okay, this is a little just, I don't even know what the word would be. It's, what is it when you have like, acronym? Is that where you have letters that stand for something, right? Remember? So, the L in Liate stands for logarithm. In other words, in this order is how we would pick our u. If we have a logarithm in there, we want that to be our u. That's our first choice. Now, let's think about why. Now, some people don't teach it this way. They just want you to understand why you're picking. Well, think about it. Our u, whatever we pick for u, we're going to do the derivative of. Well, we can do derivatives of anything. We have rules for everything. So it's easy to get du. What's hard is to get the v from the dv, right? So what do we want dv to be? We want it to be things we can easily do the antiderivative of. Well, what's the easiest thing to do the antiderivative of? Is it e to the x? It's its own antiderivative and derivative, right? So that's why e stands for exponential. We want it at the end of what to pick for u, because it's so easy to do the antiderivative of, we kind of want to leave that for the dv. And trig's pretty easy to do the antiderivative of, right? Sines and cosines are pretty easy. So right? And then algebra, like power rule. But the hardest ones to do antiderivative of are arc sine, arc cosine. That's what I stands for, is inverse. And log. We don't know the antiderivative of ln x. We don't know that. So we do not want to pick that for dv. So therefore, that wants to be our first choice for you. So logarithm is our first choice for you. Inverse trig, like arc sine, arc cosine, arc tangent, that would be our second choice for you. Algebra is kind of then next. That would be any power, like x to the 1/2 or x squared or something like that. Okay? So if there's no log or no inverse trig, then if there's an x or an x squared, then that's what we would pick for you. And then our trig would be next. That would be, if we don't have any of those others, we would pick a trig function like sine or cosine. And then exponential is the last. We would hardly ever pick an exponential for the u. That's going to, okay. So that's how we remember what do I pick for the u. All right, so let's do a problem. Now, I've actually got two of them up here, and they look very similar, right? They look very similar. They both are a product, so we don't want to get caught up too much in the fact integration by parts comes from the product rule. But most of the time, it is going to look like a product. Okay, but we've done a lot of them already that look like products. So we didn't do the product, but we did u substitution. So that's why I have this up here. What would you do on the one on the left? You would let u equal, so this is that recognition part that I'm trying to get across to you. On the one on the left, you would not want to do integration by parts. It would not work here. Because if you did, you'd let the dv be this e to the x squared. We can't do the antiderivative e to the x squared. Okay? There's no antiderivative for that. Excellent. This is a u substitution, because if you let u be the inside, then the du is your 2x dx, which, voila, is sitting right there, x dx. Right? We move the 2 over, 1/2 du. This is just a perfectly custom-made u substitution problem. The x dx would get replaced with a 1/2 du. This would be e to the u. The antiderivative of that is e to the u. So it's just 1/2 e to the x squared plus c. So I want you to understand that, again, like I said earlier, two problems can look very, very similar, but need different techniques, right? So the first thing you're going to look for is a u substitution. That's the one that's going to be the most common on the gateway, and we've done the most practice with, and we'll have the most practice on. So you always want to look for that first. Is there anything I could let u equal, right? Okay, now, so there you go. So that's that one. Now, what about this one? So now let's pretend we hadn't learned anything about integration by parts. I gave you this problem, this one. So you'd be saying, well, gee, what could you possibly let u equal here? X. It's the only kind of inside thing you have, right? Now, I think Matilda said this one day, and I don't know if everybody caught on to that. You would never, ever let u equal x in a u substitution problem. Ever. Because what would happen? All you get is the same thing. Right? du would be dx. And all you do is you just got the same integral with different letters. It didn't get you anywhere. Right? So you'd never, ever, ever in a u substitution problem let u equal x. Now, in integration by parts, though, it turns out you might. It's a different technique, right? So there is nothing you could let u equal in this to do a u substitution. There's no u you could pick so that the du would be sitting there. If you let u equal e to the x, then your du would be e to the x. You got this extra x sitting there. When we have an extra x sitting there, what do we normally do? What have we done when we have an extra x sitting there? Solve for x, right? We take our u and we solve for x, but that's not going to work here. If you let u equal e to the x, your du would be e to the x dx, and you could say, okay, I got that there, that could be a u, or that whole thing could be du. I got this extra x. Well, to solve that, you'd have a natural log. So you have an ln in there, right? If you solve that for x, then that's not going to help any. Right? So now you've got a natural log thrown in there. We don't know the antiderivative of that. So there's just nothing you could do with a u substitution. So That's your hint. Oh, well, it must be integration by parts. Must be this new thing. All right, so what did we say? We said, what do I pick for you? Log. Is there a log in there? No. Inverse trig? No. Algebra? Yeah, the x. So we're going to let u equal x. And then the dv is whatever's left over. So I usually write this off to the side. I kind of do it like a box here. I'm going to put these two here and then put the things under. So the dv is going to be everything that's left, which is the e to the x and the dx. Now the dx always goes with the dv, right? It always is going to be a leftover, right? So the dx is always going to be there, part of the leftover. Okay, well now all we need is the du, which would be the derivative of this, which is 1 dx. Don't forget that dx there. And then from the dv, we want to get v. Well, that's the antiderivative, right, to go from dv to v. So the antiderivative e to the x. Now, we don't have to put the plus c right there. We can just put the plus c on at the end when we're done. So I don't have to put the plus c right there. Okay, well now all we have to do is follow the formula. It's uv minus the integral of v du. So u times v, so that's x e to the x, right? U times v minus the integral of v is e to the x, v du. Du is just dx. Oh, it worked nicely. Look what happened. We ended up with an integral that's easy to do. So we get x e to the x minus e to the x plus c. And that's it. And you can check it. If we check it doing the derivative, what would you have to do right here? Product rule. So derivative of x is 1, e to the x left alone, plus x left alone, e to the x derivative is e to the x, and then minus derivative of e to the x is e to the x, and then the derivative c disappears, the e to the x subtracts e to the x, and sure enough, we're left with x e to the x. Okay? Now, we're not going to do a whole bunch of these. There's another technique you can use with integration by parts, kind of putting them in a box. I don't know, Steph, did you do that? You remember that with the box in e to the x? That doesn't sound familiar. Okay. So on integration by parts, there's another method you do, but that's only if you get into ones where you have a whole bunch of steps to do. Okay. And we're not going to get into any that are quite that difficult. I'm going to show you one situation that can come up. But anyway, so I think that's just a good way to do it. So notice a couple of tips here. Integration by parts probably going to happen when there's a mixture of function families. In other words, when you've got an algebra with a trig, or you've got an exponential with a trig, or something like that, where there's a mixture. Like on 23 through like 39 or whatever, they were all just algebra ones. And then you got some that just have some trig in them, and there's not really that mixture. Now, it's not always that way. Look at the one we did here. Right? Here you had an algebra mixed in with an exponential, but it was a perfect U substitution, right? So that's what we did, was U substitution. But here, you've just got an algebra, basic algebra with a basic exponential. They're going to look, it's going to be pretty easy to tell which ones are integration by parts. They're just going to look a lot different. They look simpler typically. Okay, let's do this one. Okay, let's do this one. Now again, pretty obvious. If you think about it, there's no good U substitution. There's nothing in the inside, right? Now, you could change this pretty quickly. What can I put on the inside of that log that would make this a really good U substitution? See, good. So you guys some of you are seeing that, right? An x cubed on the inside of that log would make this a really easy U substitution. Because you'd let u be the x cubed, the du would be the x squared that's on the outside, and it'd be there, and there you go. But it's not there. You let u be the x squared, the d would be 2x dx, and that doesn't help you take care of the ln at all. So this is an integration by parts. So Liate says, first pick for u is log. Oh, there is a log here. So on this one, I'm going to let u be the log. And the dv is going to be everything that's left, which is what? X squared dx. So once I decide that u substitution is not going to work, I'm going to go integration by parts, pick the u, everything that's left is a dv, and I use Liate to help me decide what to pick for the u. So now what's du? 1 over x dx. And the v, don't forget, that's antiderivative, right? So that's 1/3 x cubed. Don't have to put the plus c in there. Now, what does happen here sometimes, remember how I told you, it's nice, sometimes you get this. Let me just show you this. What if you had dv was e to the 3x dx? What's the v? Remember when you have to kick out that 1/3? I said it sure saves you a lot of work if you just know that. If when you do the antiderivative, there's a 3 on the inside, or you kick out 1/3, because you would hate to have to sit there and do a u substitution of that just to get the v. It would just take you a long time to get all that. Just nice that you know you'll kick out a 1/3 when you do that. Okay, anyway, here we raise it up to 3, divide by 3. All right, so what's our formula? uv minus the integral of v du. So uv would be these two things multiplied together. I'm going to switch them around. So I'm going to go 1/3 x cubed times ln x minus the integral. You never do anything with that. That's pretty much done then, right? I mean, the uv part is done. Then you got minus the integral of v. Now I could put that 1/3 out in front, but I'll do that in a minute. 1/3, so that's v times du. 1 over x dx. Now there's a little bit of simplifying I need to do there. I could pull this 1/3 out in front. What's x cubed times 1 over x? X squared dx. And sure enough, that has worked out well, because now I've got a simple integral to do. So I would raise that up to a 3, divide by 3, which would make 1/9, right? Multiply, 1/9. So final answer, 1/3 x cubed ln x, don't forget that first part, minus 1/9 x cubed plus c. Now this kind of violates that rule. We said that on antiderivatives, messy at the beginning and then end up looking simple at the end. Well, that's in chain rule problems. In chain rule problems that happens. On these, not quite the same, right? It's not. It ends up a little messier. But that's kind of a hint as to when you're going to use integration by parts, is when it's almost too simple looking. U substitution doesn't work, okay? There was nothing we could have picked for u, so we went with this integration by parts, okay? And again, you could work that out, and you would see that it does come out to be that. All right, a couple of interesting things that can happen with this. One of those is one like this, like arctangent, right? We said, what's the antiderivative of arctangent? We could add that to our list and make you memorize it, right? But it's one that can be done with integration by parts. Now, another one that can be done with integration by parts is natural log. We don't have an antiderivative for natural log either, okay? So, there's only one thing in there. So you wouldn't think typically integration by parts would do it. Well, you can't do u substitution because we can't turn this into like a sine over cosine or something like that because it's arctangent. That's what we did today with tangent. We did it with u substitution. Well, here we're going to do it. We're going to do integration by parts. Okay? We're going to pick the u to be Liate, right? Log first. Well, there's no log. Inverse trig is next. Is there an inverse trig there? Arctan is the inverse trig. So we're going to let u be the arctan. And we're going to let the dv be whatever's left, which is dx is the only thing that's left. You would do this same strategy for log. You would let u be the ln x, and you would let the dv be the dx. Okay, but what's du? 1 plus x squared dx. And the v would be x, right? The antiderivative of 1 would be x. Okay, so here we go. So it's going to be u times v, so it's going to be x times arctan of x minus the integral of v du. What do you get when you take x times this fraction? Just get an x on top and a 1 plus x squared on the bottom, and then a dx. Now look at that integral. Is that one we can do? How? When we let u be the bottom? Now, so that's interesting. So remember what we said. What does integration by parts do? It turns our integral that we don't know how to do into a new integral that we can do. Now, hopefully, most of the time, the new integral is just an easy one. We can just do a straight antiderivative. Most of the time, the ones I give you, that's what's going to happen. But it could be that the new integral is one we can do with another technique. In this case, we could do it with u substitution. We let u be the bottom, so I'll let you finish it out, but you can let u be the bottom. Good practice for you. We did one just like it earlier, right? That was part of that x plus 4 one that somebody asked about, right? So let u be the bottom, and away you go, and you can finish it. Okay? One last thing, and then we'll work. Okay? This one. I am not going to make you do this on the gateway test. Might happen in a homework problem. Any u substitution that sticks out? Anything on the inside or no? So this is going to be one of those integration by part. So you're going to let u equal, what do we got? We got algebra, we got exponential. X squared, right? The Leonte, the a comes before the e. So u is going to be the x squared. dv is going to be the e to the x dx. And I'm not going to go all the way through this one, but you'll see in a minute what's going to happen. So the du is going to be 2x dx. Oh, another thing I want to comment on. Never, never, never in integration by parts. You know in u substitutions, a lot of times when we end up with this 2 over here, what do we do with it? We flip it over here, don't we? Divide over. Never ever do that, right, in integration by parts. Because what we're going to end up with is we're going to want u times v minus the integral of v du. We want du to stay here by itself. So okay, because I sometimes see people doing that. You're so used to doing that when you do a du as you flip this 2 over there. We don't do that here in integration by parts. We don't, okay? Because we're plugging into uv minus the integral of v du. So we want them to stay just like they are right there. Okay? So don't do that. How many people have done that already? A few? Okay, got flat. All right. I just had a feeling. All right. Antiderivative of e to the x is e to the x. All right? E to the x. Okay. All right. So we go to our formula and we say, all right, u times v, so that'd be x squared e to the x minus the integral of v du. So that'll be, I'm gonna actually write it the other. I'm gonna write 2x e to the x, right? dx, isn't that what we'd have? 2x e to the x dx, right? v du. That we don't want to divide that 2 over there. We want v, what that equals, and what du equals. We put that there. Okay, now that 2, of course, we can move out. Okay, so let me grab that 2 out of there, and I can put that there. Now, how do we do this integral? Integration by parts again. Because what happened, our x squared, we turned it into an x, but it's, right, x to the first. Well, what will happen again? Next time we'd have it. So what if that was like x to the 6th? Yeah, I'm not going to make you do that. But technically, to get the answer, if that was x to the 6th times e to the x, you'd have to do it like 6 times. Because that x to the 6th would turn into x to the 5th, then x to the 4th, then x to the 3rd, x to the blah, blah, blah. Pretty soon it would disappear. And then you would have it. Okay. So I won't make you finish that one, but we already did that integral actually earlier. It's the first one we did, right? X e to the x. So we already actually know what the answer to that is. So sometimes you run into a situation where you have to go a couple times. You're not going to do that on gateway test. One time will be fine. But it might happen on a Okay, that's integration by parts. So rest of the time, let's do this on your assignment sheet. It says, let me see what it says for 8.1. There's not a lot of good homework problems on integration by parts. So on your assignment sheet, it says 8.1, 9 through 11, 15 through 20, and 31. And then I think in your LH, so these are integration by parts. And then these here are some more U substitutions. So in your LH packet, page 310, I would say maybe the ones that are listed on your assignment sheet, that line that says 7, 9, 16, 19, dot, 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 dot. Okay, looks like there's about 10 of them there. Everybody see that line? And do we have that packet? Is page 310 on there?
410.
Oh, I need to get you a new packet. Okay, I'll get those to you before you leave. Okay, so, all right, and those are some U substitution ones. So we get a little bit of practice of both. So the 8.1 in your book, 9 through 11, 15 through 20, and number 31 are this integration by parts. And then I'll get you this new packet here real quick, and then you can work on those. Okay? All right, rest of the time's work time. I got to get a new answer book too, because this doesn't go up to chapter 8, so I'll bring the other answer book in here.
I don't have that paper. Is it okay if I get it?
The first, that? Yeah, you, here,
Is it still on?
take this.
Thank you. Can I go use the restroom?
Yeah. Okay, there really is nothing new to give you between now and the gateway test. Okay? It's really now about practicing. So, again, those are ones. We'll do some more in class tomorrow. We'll do some more in class on Monday. But again, you got a whole big page there, 23 through 73, that LH, section 5.4. You still can be practicing some of those. Okay? And tomorrow I'm going to give you some websites. There's a couple websites, like I did with derivatives, where you can practice some of these too. Okay?